Hello and welcome back to MetaMath. In this video, I'm going to be starting a new series called Introduction to Combinatorics. We're starting at the basics. I'm going to cover all the fundamentals and gradually work my way up into covering more advanced topics in combinatorics. By the end of this series, I hope that you'll be not only more comfortable with combinatorics, but you'll be able to solve the harder problems on the AMC 8, math counts, AMC 10, and even the AIME. If you guys like this series and this video, please give this video a thumbs up and drop a comment down below letting me know what topic you guys want to see next. In this video, I'm going to be covering factorials and permutations, so let's get right into the first topic, factorials. So simply put, a factorial is just a shortcut. It's a condensed product that stands for the product of integers from 1 to n. And to translate this into more math terms, so it's easily understandable, n factorial, which is represented by the exclamation mark here, stands for n times n minus 1 times n minus 2 times n minus 3. And we keep doing this. It's the product of every integer less than or equal to n all the way up until we get to times 1. So as a concrete example, 5 factorial, we'll actually write that out. 5 times 4 times 3 times 2 times 1. That's what 5 factorial is. And now I think it should be clear why we would even use factorials. Factorials are really just a shortcut because rather than writing 5 times 4 times 3 times 2 times 1, we can use that exclamation mark, and that makes a whole lot of difference in how much work we have to do. So factorials are really useful in saving the amount of work we have to do. If we actually compute the factorial, 5 factorial, that's just going to be 120. And if we do addition with factorials, same thing, we calculate them individually, and then we can sum them together. So 2 factorial, that's just 2 times 1, so that's 2, plus 6 factorial. Now, what I'm going to do with 6 factorial is I'm going to write it in a different way. I'm going to write it as 6 times 5 factorial. And the reason why we can do that is, if you think about what 6 factorial should be, you'll know that it should be 5 factorial with a 6 in front. So basically, it's the product of all the integers less than or equal to 6 up to n. We already know what 5 factorial is, so we just have to calculate 6 times 120, which is 720. So 2 factorial plus 6 factorial is going to be 722. So that's an important usage of factorials. We can rewrite them and expand them in different ways because they're just a product of integers. So moving on from factorials, we get into our next topic, which is permutations. And what a permutation is it's an arrangement of a set where order matters. And that might be a little hard to understand, but it's just as simple as understanding where things are different. So finishing in a race first is fundamentally different than finishing in a race second or third. So how you finish, or how the people in that race finish, it matters where they place. If person A finishes first, person B finishes second, and person C finishes third, if they switched positions, C, B, A, that would be an entirely different race because the people finish in different spots. And the reason why the order matters is because, well, we assign a value to what's being placed in it. So the position in the race matters. For example, being a president versus vice president, those are two different positions, and it's important who's in what rather than if A was vice president and B was president and vice versa. So the order matters, which is very important for permutations. In another video, I'll be covering combinations, and there we'll discuss what happens when order does not matter. But for this video, we're going to be discussing permutations, which deal with order mattering. So the notation for permutations are a little bit less frequently used, and rather you'll see them in word problems rather than just explicitly written out like this. But it's good to know what they actually stand for. So when we use permutation notation, we see either of these two frequently used. And what they stand for is n permute r, and with a formula that's n factorial over n minus r factorial. And I'll explain this shortly why we could come up with a formula like this. But just applying the formula here, 6 factorial over 6 minus 4, so that's going to be 2 factorial. So 6 permute 4 is going to be 300 or 720 divided by 2, which I just said is 360. So now to understand or visualize why this is even happening, let's pretend we have 6 items. That's what our N stands for. And our R stands for the subset we're taking. So we have 4 slots. Something is what the 4 stands for the subset. So we're picking 4 of them and we want to rearrange them in that subset. So suppose that we have an index assigned to each slot. That way the order matters. Then we have 6 ways to pick the first item, 5 for the second, 4, and 3, and so on. So we have 6 times 5 times 4 times 3, and this isn't a complete factorial. However, we know that factorials are easy to work with, so we want to translate this into something that makes more sense. So we can write this as 6 factorial, but we have to realize that there's a missing 2 and a missing 1. So we just write it as 2 factorial. So the n minus r represents the difference between how many slots there are and how many items we have. And the n factorial represents how many items we have. So when we take a permutation that's less than the amount of items we have, we get this formula. If we have the same amount of items, if we had 6 items and 6 slots, well, that would just be 6 factorial, because n minus r factorial, if n equals r, would be 0 factorial. And 0 factorial is simply 1. So a permutation, we use it when order matters. And when order matters, we can simply multiply each value in the set. So we had 6 options, 5, 4, 3. We could have picked anywhere to start. We could have started here at 6. And regardless, we would have ended up with the same value. So now that we understand what permutations are and how we can use factorials, I think it's best to dive into the most common types of examples you'll see in these types of problems. So the first problem I'd like to cover is the position problem. So typically in these problems, you'll have some sort of position being available. It could be a committee, or it could be some type of office position. So here, 8 students running for 4 positions, and they're all different. So president position, vice president position, secretary position, and treasurer position. Similarly to the problem we just did, we can say that there's 8 options for the first one, for the president, but once we pick a president, there's only 7 people left who can take office. So there's 7, then 6, then 5. And again, we apply the formula, so we had 8 items, or people in this case, and we're permuting them across 4 spots or positions here. So 8 permute 4 is simply 8 times 7 times 6 times 5. And 8 times 7 times 6 times 5 is 8 times 210, which is 1,680. Now that's a really common type of position problem, and there could be restrictions, but for the most part, this is the type of position problem you'll see, which is a permutation. Now the next type of permutation problem that's fairly common is a letter problem. And in a letter problem, you have a word that has a bunch of letters. And basically what you're doing is you're rearranging the letters to create new words. The words don't actually have to make sense themselves, but you're just seeing how many possibilities you can do that. Typically, there will be restrictions on the letters themselves. For example, they might put a restriction that the M's have to be next to each other, but the idea still sticks together with whatever type of letter problem there is. So we have 8 letters, and we want to rearrange them. So the subset is 8. 8 slots because we want to use all 8 letters. So it's really just 8 permute 8, which you might think is 8 factorial. But we have to take into account that we have 2 identical M's, we have 2 identical T's, and we have 2 identical A's. And they're identical because we can't tell the difference. There's an A right here and an A right here, and if we swap the positions of those 2 A's, we wouldn't be able to tell the difference. So ultimately, this boils down to how do we account for the fact that there's 2 identical of these 3 letters? Well, we just think about if there's 2 M's, we switch the position, we get 2 orderings, but only one of the positions or orderings is what we want to count. So for every 2 orderings we have, only one we want to count, because otherwise we're just overcounting the same thing. So we have to multiply by 1/2 for each letter that there's an identical copy. So to do this, we account for the fact that there's 3 identical letters. So 8 factorial divided by 2, divided by 2, and divided by 2. And that's simply just 7 factorial. 7 factorial, if you think about 7 times 720, that's 4,900 plus 140, which is 5,040. So that's how many ways there are to rearrange the letters in meta math when we account for the fact that there's certain restrictions. The M's, the T's, and the A's are repeated, and this is a very common type of permutation with restriction and repetition. And the last type of problem I want to discuss is the shelf problems. And these are all very similar to the previous problems, but this is a specifically harder one. This is a 2016 AMC 8 problem number 16. And this problem involves books on a shelf. And again, we're going to have 9 books, and we have to take a subset that is also 9 books. So we're going to be permuting across the same set. The issue here is that we have multiple copies, 2 Arabic, 3 German, and 4 Spanish. So we have to take that into account. And you might be thinking that we simply just divide by 4 factorial, 3 factorial, and 2 factorial like we did in the previous problem. However, the issue here is that the books are fundamentally different. You can tell 2 Spanish books apart from each other, but you can't tell 2 letters apart from each other if they're the same. So because you can tell 2 Spanish books apart, you have to account for that by multiplying. So if I have Arabic book 1 here and Arabic book 2 here, if I switch the positions, they would be distinguishable. And for that reason, we have to account for the fact that they're both different orderings. So we don't have to divide by 2 here. But if we look at what the problem is putting on, the restrictions, the Arabic books have to be together and the Spanish books have to be together. And a common tactic for dealing with this condition of togetherness, when you have 2 things or more than 2 things that have to be together, is to combine them. And what I mean by combining them is to assume that they're stuck together. Pretend that these 2 A's form a big A and that they're stuck together. And likewise, assume that the 4 S's in the 4 Spanish books form one giant Spanish book and that they're all stuck together. What we're left with is a giant A, 3 German books, and a giant Spanish book. Now, this is more manageable here. We have 5 books. So that's 5 factorial, and we should be done. But we have to account for the fact that even though we transform the 4 Spanish books into a mega Spanish book, within that subgroup, we can arrange it in a subset. We're permuting 4 Spanish books across 4 slots. So that's going to be 4 factorial ways to arrange the Spanish books inside of that giant Spanish book. We could do S1, S2, S3, S4, or we could do S2, S3, S1, S4. So there's 4 factorial ways we can arrange the Spanish books, and likewise, 2 permute 2 gives us 2 factorial ways to arrange the Arabic books. So 5 factorial times 4 factorial for the Spanish books times 2 factorial for the Arabic books. We don't have to multiply by 3 factorial for the German books because they are not together, so we can naturally split them apart if necessary. So what we have to calculate is 120 times 24 times 2. We can move the 2 to the 120 to get 240 times 24. 24 squared is 576 times 10 from the 0 is 5,760. So there are 5,760 ways to arrange the books, the 9 books on the shelf, if you keep the Arabic books together and the Spanish books together. Now this wraps it up for this video on combinatorics, introduction, specifically factorials, and permutation. In the upcoming videos, I'll discuss more advanced topics like combinations, but if you found this video useful, please give this a thumbs up and drop a comment down below. See you guys in the next video.